So today we'll talk about heat and heat transfer. So heat, which we'll symbolize with the letter Q, naturally, is the spontaneous transfer of, the spontaneous transfer of energy due to temperature difference, right? So heat is a form of energy. It's kind of long and short of it. So just be careful. Commonly, it's easy to confuse heat with temperature. They're two different things, right? So we might say, oh, it's really hot out, the heat's unbearable, but what we actually means the temperature is high, right? Because heat's energy and temperature is not energy. So that's just something we use in our language just to be careful with. When we're dealing with heat, we're dealing with our SI unit of a joule, so we'll use J to symbolize joule. And another unit you might have used, especially in chemistry class, would be the calorie or kilocalorie. So looking at this here, let's suppose we've got a soda can here and a block of ice. These two objects are in situation A are in different temperatures. They are not in thermal equilibrium. In situation B, both these objects are now in thermal contact with each other, meaning that heat's going to transfer up to the point in which they're going to have the same temperature, right? So this is going to be called thermal equilibrium. So heat transfer is going to occur because of the difference in temperature between the two substances. Now, we can also change the temperature of an object by doing work. And when I say work, I literally mean the work we studied in mechanics. So work being effectively force times distance, among other things. So here we can use work to actually add energy to our system or take away energy from our system. Actually, the person who showed this was Joule, which is why the unit for heat is named after this person. He established what's called the mechanical equivalent of heat. So basically, this is the amount of work needed to produce the same effect as heat transfer. So we have this kind of conversion, if you will, that 1 kilocalorie of work is the same as 4,186 joules. And the way he kind of discovered this was actually through this kind of crazy experiment. Kind of has a setup here on the right. This is one of his more famous experiments. I got this off of Wikipedia. But basically, he demonstrated here that work and heat produce the same effects. And this basically helped establish the idea of conservation of energy. So the way he kind of went about doing this was he had a hand crank here, in which would then cause these weights to then rise and lower. So he can measure the amount of work done on these weights. And this also translated to these little paddles inside the fluid here. Here I have water. And cause these paddles to move, causing an increase in kinetic energy and therefore a change in temperature. An increase in temperature, because remember, temperature is directly proportional to kinetic energy. So he was able to then basically measure the amount of temperature increase and relate that to the amount of work done, and therefore relate it to the amount of calories. It's pretty interesting. Alright, so when we add or remove heat from a system, it's going to change its value for internal energy, and therefore its temperature. So what's an example of this that you've experienced in your everyday life? Also, does adding heat always lead to an increase in temperature? So there's many different examples you could give, but kind of the easiest one might be cooking, right? So for, let's say you're trying to increase the temperature of some soup you're cooking, you're going to add heat to do that. Now, adding heat does not necessarily mean you're going to have an increase in temperature. So an example of this would be during phase change. So during phase change, the temperature of the substance stays the same, but you can still add or remove heat. In fact, you need to, otherwise the molecules cannot change form. So let's suppose we had two samples of some same substance that are kept in the lab. Let's assume that to one substance we add 10 kilojoules of heat, while the other one, let's do 10 kilojoules of work done on it. How can you tell what sample heat was added and which one was work done? So that was a trick question. They're both going to change the internal energy of the substance, right? But it's going to be impossible to tell whether heat was added or if work was done. There's no physical way you could determine that. All right. So whenever we have a temperature difference, heat transfer is going to occur. Now, how fast this heat transfer occurs depends on the substance, right? Substances can have heat transfer pretty quickly, like the metal used in a cooking pan, or it could cause heat transfer to be slow. So, for example, a cooler that you're using to hold ice or something like that. There's a big industry in kind of thinking about materials and how well they conduct or how well they don't conduct heat, and how that's important. So, for example, if we're designing clothing for winter, we're going to choose something like wool, which causes heat transfer to be slower than compared to, I don't know, something with a bunch of holes in it. So that kind of idea. Now, when we're talking about heat transfer, we categorize it into 3 different ways. So heat can transfer 3 ways. They're going to be conduction, convection, and radiation. So I'm going to briefly introduce each of these topics now, and then actually focus a bit more on conduction, since that seems to be a focus in the AP exam. So conduction is heat transfer through stationary matter by physical contact. Right? So we've got 2 objects in contact with each other and heat transfers between them. So that's conduction. So an example of this would be, let's say, an electric burner on a stove and a pan on top of it. So heat's transferred to the pan from the stove through direct contact. So that's conduction. Sorry, it's kind of loud. All right, so we also have convection. This is heat transfer through the movement of a fluid. Right, so this would be, a lot of times we're talking about air when we're talking about this fluid, but it could also be water. So maybe, for example, maybe you have a fancy computer system and you use water as a cooling substance here. So heat is removed from the mechanical parts of your computer through the water. So this would be a fluid. So this is convection. Right, so this also occurs when you're dealing with, let's say, a forced air furnace, or more broadly in weather systems. So this convection is what causes different weather patterns that we experience. And the third way we can have heat transfer is called radiation. Right, so this is going to be occurring. This is the heat transfer through basically electromagnetic radiation, so light. Whether or not that's visible light doesn't matter. So typically this is going to be in the form of microwaves, infrared waves, in a visible spectrum of light, and amongst other things. So in a kind of a very obvious example of this is the Earth being warmed by the sun. Right, so the sun is emitting not only just visible rays, but also other. I don't want to get too much into the electromagnetic spectrum because we're going to talk about it later, but basically it emits both visible light and non-visible light, which then causes the Earth to have heat, which is good. That's why we're here. Now, kind of a less obvious example is going to be the thermal radiation that you give off, right? Your body is warm. You can probably, I don't know why I don't have a picture here, but you've got thermal imaging you can do of bodies and things, where you have like the different colors associated with how hot or cold something is. So kind of an example here in which we have all 3 forms of heat transfer is going to be, let's say, this fire pit. So we've got radiation, so we see that there's visible light being emitted, also other types of light rays as well, but you can have heat be emitted from that. You also have conduction, so here we have a metal poker literally touching the fire and the wood here. So that heats up. And we also have convection, so the air around the fire heats up and warms things around it by that reason. Similarly, we can have air, we can have, what are the words I want to use here? If you have a fireplace in your house, it's actually pretty interesting. We've got all different types of heat transfer here as well, right? We've got heat from the radiation of the light from the fire itself. We've got convection in twofold. We've got convection up, hot air leading through the chimney, but we also have then cold air coming from other parts of the house. And also we've got conduction, so it's going to be the heat kind of through the floorboards here. So kind of the most amount of heat that you feel when you light a fire in your house is going to be the radiation heat, or the heat transferred through radiation, excuse me. Where actually you'll notice that other parts of your house are going to get colder because you lit a fire, let's say, in the living room. And that's because convection's occurring, causing the cold air to, or causing that part of the room, other rooms to be, have cold air kind of come into it. Man, I could have worded that better, but I don't have enough time to go over it. But anyway, I think that's actually where I'm gonna stop here. I hope that was helpful.